Today's video is on graphical behavior, and we will be looking at the graphs of functions to determine domain and range, increasing, decreasing, or constant, as well as the concavity of the curve and any discontinuities or end behavior. We will also look for the extrema and points of inflection. For part one, we're going to go through and find the domain and range of our functions. So in example one, the domain is the set of x values that exist for the curve. And if we think about our leftmost x value, which is located here, our leftmost x value is -4. And we put a hard bracket on it because it is a closed circle. As we move to the right, the function exists, it exists, it exists, and it keeps existing forever and forever to the right, all the way out to infinity. So the domain is the x values that exist on the curve. If we wanted to express this as a set, we could say all x greater than or equal to -4. However, I will be using the interval notation for the discussion of domain and range. Let's look at example 2. In example 2, the leftmost portion of the graph is all the way out at -infinity. You can see the graph keeps moving to the left. And the rightmost portion of the graph is all the way out at +infinity. So the graph exists all the way from -infinity to +infinity, except there is a discontinuity at -2. So our graph will have a domain from -infinity to -2 in union with -2 to infinity. This discontinuity is a vertical asymptote. Infinities get soft parentheses. Example 3. This is a case again where the function moves to the left forever, so our lower bound is going to be -infinity. And our upper bound, the curve does move to the right forever, will be +infinity, but the graph does have a hole at -3, so we are going to put a gap in our domain at -3 to show that there exists a discontinuity there. Let's look at example 4. The domain, the lowest x value, this curve keeps moving up and to the left, as well as up and to the right. So the domain has no gaps. We can say it goes from -infinity to +infinity, or if we want to use the symbol for the set of all real numbers, that would work as well. Let's look at example 5. Example 5, the domain starts. Our lowest x value is at -8, and then our highest x value keeps going all the way out to infinity, and it looks like we have two discontinuities that exist. We have that jump discontinuity happening at -4, and the hole at 2. So we're going to have those two discontinuities to account for in our domain. So our domain starts at -8, inclusive. Then we have the jump at -4. Then we have the hole at 2. And then we have the continuation of the domain from 2 to infinity. Let's try example 6. Here we have another polynomial. There's no holes or jumps or asymptotes in it. The leftmost portion of the graph is all the way out at -infinity. The rightmost portion of the graph is all the way out at +infinity. So this is another example where the domain is all real numbers, or the set of -infinity to +infinity. Let's look at example 7. Okay, in example 7, our leftmost point happens at -3 and is an open circle, so that means it is not included in the domain. And then as we move along, our rightmost point is going to be at +5, and that +5 has a closed circle at it. If we look at where the jump exists, we would want to exclude the jump if this was an open circle and an open circle. But since this jump is directly on top of one another, this value of 3 actually is part of the domain, and so we don't need to split our domain there, and we can go simply from -3 all the way out to 1, 2, 3, 4, 5, all the way out to 5. Close bracket on the 5 because it's a closed coordinate. On to example 8. The leftmost portion of the graph happens at -4, and the rightmost portion of the graph happens at +4. There's no arrows on either side. Both of them are closed circles, so they will get closed brackets. And then we have to deal with the discontinuities, and in this case there is a jump here with 2 open circles, so we know that there's definitely a discontinuity that's going to break our domain there. And then this jump goes from a closed circle to an open circle, and because it's directly on top of one another, we don't need to split the domain there because the value 3 is accounted for in the domain. So the domain goes from -4 to -1 in union with -1 to +4. Let's look at example 9. What we have here is the graph of what appears to be another polynomial. The arrows go leftward and rightward forever. So our leftmost bound is -infinity and our rightmost bound is +infinity. And we get the domain of all real numbers. There is no gaps along the way, so either the interval notation or the set notation for all real numbers. Let's look at example 10. Example 10, I apologize for the small numbers, they're kind of hard to read, but this arrow here keeps going to the left, so we know that the function is going to have a lower bound of -infinity. Then we have an open circle here and a closed circle here, so there's going to be no gap there. There is a gap where the vertical asymptote occurs, which is at +2. There's another gap where the hole occurs, which is at +3. And then finally the curve continues to exist forever rightward all the way out to infinity, so 3 to infinity. And we get 3 separate regions for the graph, even though it is kind of composed of 4 pieces. Moving on to example 11. Let's get this wild, crazy graph here. Our leftmost point is at -5, and our rightmost point is at +5. Those are both closed circles, so they will get hard brackets. This gap here gets filled by that hole. This gap here is filled by that hole. We do have a gap at 0, so that's a discontinuity we need to account for. Then we continue to exist, and then we have an asymptote at 3. So what we have is 3 regions, -5 to 0, in union with 0 to 3, in union with 3 to 5. And finally, let's look at the last example, example 12. Another case here where the endpoints are both closed, so we can do hard brackets on the left side and the right side. Then we look for any gaps. As our pen moves along, the first gap happens here, but it is picked up by a closed circle. Then the next gap happens at -1, and there is no circle to close it. So that'll be a discontinuity. Then we have a jump occurring here, but the closed circle maintains that domain at that number. And then we have the vertical asymptote, and that splits the domain. So again, we have a case of 3 regions. We go from -5 to the whole at -1, and then from -1 to 3 where the vertical asymptote exists, and then 3 to 5 where the right endpoint exists. That's domain. Let's take a look at these same 12 functions and discuss range. Range is going to be similar to domain in the sense that we express our answer as an interval, or we can do a set, but I favor the interval notation, except now instead of looking at x coordinates, we're going to look at the y coordinates of the function. And so when I'm looking at this function, the lowest y coordinate that I see is here at -3, and the highest y coordinate that I see, the graph continues up and up and up and up and up, so the highest y coordinate is at infinity. So my range goes from -3 all the way up to infinity, and those are y values. Let's look at the second graph, example 2. In example 2, we have a case where the curve goes downward and downward and downward. So this curve keeps going down, or on this side, but because the graph goes down forever, our lower boundary is going to be down here at -infinity, and our upper boundary, because the graph goes up forever, our upper boundary is at +infinity. So those are y values of approaching -infinity and a y value of approaching +infinity. If we wanted to express this as all real numbers, that set notation works as well for range. Let's look at example 3. Okay, so our curve has the lowest y value as of -infinity and the highest y value of +2, and it actually touches that 2, so we'll do a hard bracket on that. And then if we find any gaps in the y, we'll need to break our range. And there's a gap right there, however, it does get picked up with this y coordinate. So the curve has all y values from -infinity up to +2 inclusive. Let's look at example 4. The lowest y value in this graph is at this point right here, which is kind of hard to read, but let's call that point at -35. Kind of eyeballing it, but we'll go with -35 as our lowest y value. I'm going to say it comes all the way down and touches that point. And then the highest y value, since both endpoints go up forever, the highest y value is going to be up at infinity, and there's no gaps between those two numbers. I guess infinity is not a number, but there's no gaps, so our range is one set, the set from -35 inclusive to +infinity. Let's look at example 5. Looking at this graph, the lowest y value comes from this arrow, which goes down forever and ever and ever. So our lowest y value is -infinity. The highest y value that we see is up here at 6. And then we want to see if there's any gaps. And so this is all continuous up to that point, and we have continuity from 4 to 6. So all y values are accounted for. This gap here is picked up at that location. This gap here is picked up at that location. So we're good all the way from negative infinity up to 6. Example 6. Have another polynomial here. Low point is a little difficult to read, so I'm going to put a tick mark roughly where that low point is, and I'm going to call that low point negative 175. So negative 175. The ends go up forever, so the upper boundary will be unbounded or going to infinity. And there is no gaps in the y aspect, so the range is negative 175 up to infinity. Let's look at example 7. This is a good example for range. I like this one. So the lowest y value that I see is at negative 5. Yes, it doesn't exist here, but it does exist there. So our lower boundary starts at negative 5. And then as we move up, there's a spot starting at 3 going until, negative 3 going until negative 1, where the graph doesn't exist in the y area. So we're going to have a jump in our range from negative 3 up to negative 1. And then the function exists all the way up to a max height of positive 5, which gets a closed bracket because it's a closed circle. So that's example 7. Let's look at example 8. Our lowest y value is negative 2. Then we have y values up to 1, and we're going to close it at 1. So that area from negative 2 up to positive 1 accounts for these two sections. And then there's a gap, and that gap picks up again at positive 2 and finishes at positive 4. Okay. So positive 2 to positive 4. I'm just going to reuse these arrows because it's the same parenthesis set. Example 9. Example 9, we see an arrow that goes down forever and an arrow that goes up forever. There is no gap between, so negative infinity to positive infinity. This polynomial has an infinite range. All polynomials of odd degrees would have an infinite range because one end points up and the other end points down. Let's move to example 10. Example 10, the lowest y value the graph has occurs at negative 3, and it never touches that horizontal asymptote. It gets closer and closer to it, but it never touches it. So we're going to put a soft parenthesis on that. The highest y value that the graph has is at positive infinity, because the graph keeps going up and up and up. And we need to check to see if there's any gaps as we move our way up. And as we move our way up, there is a gap at a y value of negative 1, and then it's continuous forever onwards. So that hole splits the range at negative 1. Let's look at example 11. Example 11 is a pretty wonky graph, but let's see what we can do. The lowest spot is at negative infinity, because we have these two arrows pointing down to negative infinity. Then as we accumulate y values, There wants to be a gap there, but it's picked up at 2 locations, so we keep going up to a y value of 1. So at 1, we're going to break our y values. We'll assume that it actually goes up and touches that height. Then we have a gap up to a y value of 2. Because there's an open circle there, I'm going to say that the graph gets really close to 2 but does not touch it. And then we have y values continuing onward up to a height of 4. And the closed circle at 4 tells us that there is a hard bracket on 4. Crazy looking graph, not too difficult looking range. All right, let's look at example 12. Example 12 is another example of something that looks crazy but actually is pretty easy to do. The lowest y value is down at negative infinity, and the highest y value is at positive infinity, and we just want to see if there is any gaps in between, and there is no gaps because this hole is picked up by that portion of the graph, this hole is picked up by that portion of the graph, this hole is picked up by that portion of the graph. So we have all numbers from negative infinity to infinity, or we could say the set of all real numbers. All right, this concludes the portion of the video on domain and range. All right, welcome to part 2 on our video series on graphical behavior. In this part of the series, we're going to be looking at increasing, decreasing, and constant behavior. Increasing functions are functions that are moving uphill as we move from left to right. So the uphill process I'm going to highlight in orange to help us define the region or the domain for which the function is increasing. So when I look at this graph, there is 2 intervals for where the function is increasing. That interval is from -2 to 0 in union with 2 to infinity. And these are domain intervals, so these are the x-coordinates for which the function is increasing. Decreasing is generally the complement to increasing if there's no areas where the graph is constant. And the decreasing I'm not going to highlight, it's this portion that's black or unhighlighted. So the leftmost area is -4 to -2 in union with 0 to 2. And this should add up with constant to our domain. The graph is constant nowhere, so I'm just going to write that here. And the union of these sets should lend itself to be similar as the domain, especially if we used hard brackets. I will always use open intervals for increasing and decreasing, so we don't have to worry about hard brackets versus soft parentheses. And that is consistent with my experience with the AP calculus test. The justification where I said it's where the function is going uphill is kind of a loose definition. A more formal definition is found in calculus class. A function is increasing when the derivative is greater than 0. And we do an analytic approach when we have the function rule. But graphically, you can think of it as going uphill. Let's look at example 2. As I move left to right, the function is going uphill left to right, and then again uphill left to right. And so this function is increasing everywhere except at that asymptote. So -infinity to -2 in union with 2 to infinity. Nowhere is this function decreasing, and nowhere is this function constant. Let's look at example 3. Increasing from left to right, increasing from left to right, down, 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 increasing from left to right, and out towards the end, it's still increasing, but it's increasing very, very slowly. So we've got 3 regions, one being split by the whole and the other being split by the decreasing area. So we've got negative infinity to negative 3 in union with negative 3 to negative 2 in union with 0 to infinity. The decreasing region is from negative 2 to 0. We'll put that negative 2 to 0. And there's no regions where the graph is constant. Constant would be flat portions in the graph, which we will see in one of our examples, hopefully. Oh my, I have avoided including a graph that has a constant area. So let's real quick this graph here is increasing, constant, increasing. Large oversight on my worksheet not to include constant regions. But okay, let's look at example 4. A little bit busier of a graph. We've got going uphill, and going uphill. So on this graph, we could say that we're increasing from this location to this location, and that appears to be at 1. This number is a little more elusive. We'll go with from negative 2.5 to 1 in union with 2 to infinity. In calculus class, we might make a distinction and split it here at negative 1. It really depends on what's going on at a much deeper level than we examine in pre-calculus at that location. But for all intents and purposes, this is going uphill for pre-calculus students. Example 5. Wait, before we move to example 5, we should finish this up. Decreasing from negative infinity to negative 2.5 in union with 1 to 2. Constant nowhere. Okay, now we'll look at example 5. Increasing, we have this portion of the graph that's going uphill and this portion of the graph that's going uphill. So we got 2 spots where we're going uphill. Those go from x equals negative 4 to 0 in union with 2 to 4. So we're only looking at the x values, remember. Decreasing would be going from negative 8 to negative 4 in union with 0 to 2 in union with 4 to infinity. And if we had a flat spot on this graph, we'd have a constant area. But I have omitted that due to an oversight. Whoops. Example 6. Where is the function increasing? Well, we've got the region right here. And we've got this region and this region. So it looks like we have two or three intervals of increasing. We have the first one from negative 3 to negative 2. And then we also have I don't know, maybe that's at 1.5. To, if we don't break this at 4 and we just assume it's going uphill the entire time, to infinity. The decreasing region would be from x equals negative infinity, or near negative infinity, to -3, in union with -2 to the number which we declared was 1.5. Let's look at example 7. The increasing area is that region and this region. So we have two intervals of increasing from x equals -1 to x equals 3 in union with x equals 3 to x equals 4. Decreasing would be the unhighlighted region, which is -3 to -1 in union with 4 to 5. Constant nowhere. Example 8. Increasing regions. Well, we're going downhill. This is uphill as we move left to right, and this is uphill as we move left to right. So we've got two increasing intervals. One goes from x equals -1 to x equals 3, and the other one goes from x equals 3 to x equals 4. This region is decreasing starting at x equals -4 and decreases to x equals -1. Constant nowhere. On to example 9. A little bit busier, but we've got uphill behavior, uphill behavior, uphill behavior, and uphill behavior. So those are all of our increasing regions. The leftmost spot is at -infinity. Then we continue to -3. Our second region goes from -1 to, we'll say 0.75. And then our third region goes from 3 to infinity. This makes the decreasing region -3 to -1 in union with 0.75 to 3. See how we're increasing, decreasing, increasing, decreasing, increasing. We have no constants. In calculus, the definition of a constant is the derivative equals 0. So one could argue that we have points of constant behavior, but I wouldn't equate that, at least in pre-calculus class. That's getting into the nitty-gritty details. On to example 10. Uphill from left to right. Uphill from left to right. Uphill from left to right. So we got those two regions that are going uphill. The first region goes from the left -infinity to the right of 0 in union with the second region goes from left of 0 to the asymptote at 2. The decreasing region is the part that's going downhill, and we do have to account for that hole right there. So we have decreasing from x equals 2 to x equals 3, in union with x equals 3 to infinity. Remember, these are all x coordinates, and then constant nowhere. Example 11. All right, pretty busy graph here in example 11 and 12, but let's still do it. Increasing is uphill behavior. And we have 4 regions of uphill behavior. So we go from negative, not 3, that should be negative 4. Negative 4 to negative 2, in union with negative 2 to 0, in union with 0 to 1, and union with 3 to 4. Very busy graph. Lots going on there. Decreasing would be negative 5 to negative 4, as well as 1 to 3. 1 to 3. And then finally this last little bit, x equals 4 to x equals 5. Okay. Example 12. Increasing. Uphill, uphill, uphill. All right, looks like we only have 3 uphill regions. The first region goes from x equals negative 5 to x equals negative 4. The second region goes from x equals negative 3 to x equals negative 2. And then the third region is from negative 2 to negative 1. Decreasing areas goes from negative 1 to positive 1, in union with positive 1 to positive 3, in union with positive 3 to positive 5. Again, we always use open intervals to discuss increasing, decreasing, and constant. And I forgot to write nowhere on the last one, but that's because I didn't give an example of a or a constant graph. So again, if I had one last graph to include here, this one is increasing from negative infinity to 0. This is decreasing from 0 to 1. And this is constant from 1 to infinity. Okay, so the constant area is where we are neither increasing nor decreasing. All right, that concludes the portion on increasing, decreasing behavior. Thanks for watching this portion of the video, and we're going to move up to concavity next. Welcome to the third part of our video series on graphical behavior. In this video, we will be looking at regions of a graph that are concave up or concave down, as well as the point or points of inflection. Now, concave up is referring to a portion of a graph that opens upward. You could say it's concave up like a cup, versus concave down, where it opens downward, concave down like a frown. And I will be highlighting the region of the graph that is concave up in orange. So when I look at this first graph, the curve is concave up to about there and concave up on that entire region. The exact location where it transitions is a little bit harder to determine visually, but those points where it transitions, those are called points of inflection. And it takes some calculus skills to find the exact locations of those oftentimes. So our first point of inflection, we're going to call this at, we'll go with 0.75 comma 0 is the coordinate, and the second one we'll go with the coordinate, I don't know, x equals 1, y equals 0.25. I'll try to create points of inflection that happen on the lattice points, but for now, those are x-y coordinate pairs. And so that is not an interval. But the concave up and concave down area, those are intervals. So this interval goes from the x value of -4 to the x value of, we determined, -0.75. That was a mistake down here. -0.75. As well as the x value 1 to infinity. Concavity is definitely a harder thing to find sometimes. It's not as clear cut as increasing, decreasing. Concave down would be the region in the middle, which is from -0.75 to 1. Okay. So hopefully our future graphs are a little more clear. Like here we have an example 2. We have a curve that is kind of like the right hand side of a concave up cup. So we've got concave up from -infinity to -2. And then the second portion of the graph looks more like a frown, concave down like a frown from -2 to infinity. This graph has no points of inflection, and I don't even actually ask it on this part of the worksheet, but let's look at example 3. Okay. In example 3, I've got the cup shape happening in the middle, and then the rest of that area looks like it's facing downward. So we've got the concave up going from -1 to 1, and then these three regions are all opening downward. So we've got 3 concave downs from -infinity to -3 in union with -3 to -1 in union with 1 to infinity. And we have 2 points where the concavity changes. And so we'll list those 2 points. The first point is at x -1, y +1. And the second one is at x 1, y 0. So remember, these are not intervals, but they're x, y coordinates. Okay. Example 4. Oh boy, there's a lot going on in this one. This is a polynomial. This region is concave up to somewhere in the middle there. And then we've got, again, concave up to somewhere in the middle there. And then somewhere in the middle, that region is concave up. This really highlights the importance of calculus being a tool for discovering concavity. We really start to dive into how to exactly locate where there's a switch of concavity. Another definition for concavity has to do with tangent lines. And when you have a curve that's concave up, tangent lines are below the curve. And when it's concave down, tangent lines are above the curve. We don't need to know that for pre-calculus. Concave up. Our first interval goes from negative infinity to, we'll say, -2. Our second interval goes from -1 to, let's go with right there being 0.25. Our third one goes from, we'll go with 1.5 to infinity. So I'm kind of eyeballing those numbers. Concave down would be generally the complement to it. So we have concave down from -2 to -1, as well as 0.25 to 1.5. Curves can express no concavity, and that would be a case where the curve is a straight line. Straight lines do not have concavity. And we see that in example 5. So example 5, there is no concavity here because it's a straight line. No concavity, no concavity. And the only region where there is concavity is a concave down region. So that region starts at x equals 2 and continues to be concave down all the way out to x equals infinity. Example 6. Another polynomial here with a lot going on. The first half of the graph is concave up. Then we have some concave down behavior. Somewhere along the way, it makes a transition to concave up. Then it transitions to concave down, and then it transitions to concave up. So the exact location of the transition point, as I've said, is kind of difficult to see with the eye. We really need to analyze the equation to find that point. But let's write down what approximately we see. Concave up from -infinity to probably -2.5. In union with, we'll go -0.5 to (2.5), and then finally 4 to infinity. The concave down region are those two black regions, being from -2.5 to -0.5, in union with +2.5 to +4. All right, let's look at example 7. Straightforward, simple curve here. We've got one portion that is concave up and one portion that is concave down. So the concave up goes from x equals -3 to x equals +3, and the concave down goes from x equals +3 to x equals +5. Okay. Example 8. These two regions are straight lines, so they express no concavity, and then this graph has two portions. We'll split it right in the middle, and the concave up portion is right there. So concave up is from -2.5 to -1, and the concave down is from -4 to -2.5. So our point of inflection, that would be a point of inflection. Okay. I guess I didn't do point of inflection on this graph here. Because there is a change of concavity from concave up to concave down, and the graph is expressed at x equals 3, one could argue that 3, 5 is a point of inflection because a point of inflection is a point that exists where concavity changes. I think because there's a jump at that point, that this is kind of a debatable point of inflection. I've tried to find a very precise definition of whether or not you would call that a point of inflection. And even going to forums, I've had kind of mixed opinions on it. My professional opinion is that I would not include it as one because the function is not continuous there. So I'm going to say no, but if you included it as a point of inflection on the test, then I would give you credit because you're getting the concept. Example 9, another polynomial here. Going with some concave up regions. Got a very short-lived stretch there. Got another stretch right here. And then another stretch right there. So there's 3 concave up regions. We'll go with -5 to -4. Next one goes from -2 to 0. And then the last one goes from about 1.5 to infinity. This leaves 3 concave down regions. This one over here, almost overlooked. -infinity to -5. Then the gap here, -4 to -2. And then the gap here, 0 to 1.5. So visually it looks like we have 1, 2, 3, 4, 5 points of inflection. So that first point of inflection is at -5, 0. The second point of inflection is at -4, 25-ish. Then we have one at -2, 20-ish. Then we have one at 0, 10, and another one at 1.5, 10. 1.5, 10. Okay. Example 10. Concave up, we highlight. That part is concave up. This part is concave up. This part is concave up, and this part is concave up. So this graph is concave up everywhere on the domain. Every single spot. So there is no spot where it's concave down. So I will go ahead and write that. Concave down nowhere. And concave up should match our domain, which is -infinity to 0 in union with 0 to 2 in union with 2 to 3 in union with 3 to infinity. Two more examples. Example 11. Get into the crazy busy graphs here. Example 11, concave up and up, 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 up to a transition, and then those two regions are down. So it looks like we have 1, 2, 3, 4, 5 concave up areas. -5 to -4, -4 to -3, -3 to, did I count that wrong? 1, 2, oh, that's not a 3, that's a 2. -4 to -2, in union with -2 to 0, in union with 0 to 1, in union with 1 to 2. Pretty busy on the concave up. Concave down, we only have two regions, being from 2 to 3, as well as 3 to 5. This leaves one point of inflection where the concavity changed. So that point of inflection happens at 2, -1. Remember, these are xy coordinate pairs as opposed to up here where these are intervals. So add x equals 2, y equals -1. All right, last example. Example 12. Concave up. This interval. Down, 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 up. Okay, we've got two concave up intervals. -4 to x equals -2, in union with x equals 3 to x equals 5. The concave down intervals are -5 to -4, and then -2 to -1, -1 to +1, and finally 1 to 3. There is one point of inflection for this graph, and that point of inflection happens at that location right there because we go from concave down to concave up. This is an arguable point of inflection. Again, I think because the curve is not continuous through that concavity change, I would say it is not a point of inflection. But as I have said, if you did include that one, you get the concept and I would award you credit. If anybody knows and wants to point that out as a comment, I would really like to know the precise definition that would tell me whether or not that is a point of inflection. Every textbook I've looked at doesn't give enough information to discuss concavity changes at discontinuities. All right, that concludes the portion on concavity. Thanks for watching this video. We'll be looking at discontinuities next. All right, welcome to part 4 on the video of graphical behavior or video series. In this portion we will be looking at discontinuities and end behavior. And this should be a little bit quicker than the other videos, so let's roll. Discontinuities are where you have to lift the pen when drawing the graph, and as I trace this graph I never had to lift the pen, so there are no discontinuities, or there are none. This is an endpoint, but it is not a discontinuity. Left end behavior is asking the question, as x goes to -infinity, what does the function tend towards? And some people put an equal sign, some people put an arrow. I'm going to be using the equal sign. On the left-hand side, the graph doesn't exist out towards negative infinity, so the left-end behavior does not exist, or the limit as x goes to negative infinity does not exist. So going towards the right-hand side, or as x approaches positive infinity, what does the function approach? Well, as x goes to infinity, y tends towards positive infinity. And this is why there's a little bit of debate about whether or not to use an equal sign or an arrow. We can't really say something equals infinity because, well, infinity is not a number. So there are some people who prefer the arrow. And honestly, I prefer the arrow, but I just haven't built the habit of writing the arrow. And likewise, we can't really say equals does not exist. We can say it tends towards not existing. The function doesn't exist over there. Okay. So that's your end behavior. Incidentally, for end behavior, left end behavior will always start with this same expression, and right end behavior will always start with that. The name of the function might change. You might have the function being named g of x or h of x, but okay, let's look at the second example. Discontinuities. As I'm drawing from left to right, I have to lift my pen at the asymptote and then continue on. So there is a discontinuity. Specifically, it is a infinite discontinuity located at x equals negative 2. There's a vertical asymptote. One or both of the sides approach infinity. My left end behavior, as x goes further and further to the left, the function goes further towards negative infinity. If I take the right side limit, as x goes further to the right, the function climbs and climbs and climbs towards positive infinity. Let's look at example 3. Discontinuities. As I'm drawing along, I have to lift my pen at the hole that is located right here. So we have a hole at x equals negative 3. And then the pen stays on the paper for the rest of the graph, so that's the only discontinuity. In a calculus class or late pre-calculus, we'll start to talk about limits to discuss the more formal definition of a discontinuity. But the left end behavior of the function and the right end behavior of the function, those are always going to be written exactly the same. The left side, as we go further and further to the left, it tends towards negative infinity. And if we go further and further towards the right, it tends towards a value of 1. Let's look at example 4. This is a polynomial, and polynomials are continuous everywhere. I never had to lift my pen at all drawing it, so this has no discontinuities. There are none. The left end behavior, as we approach negative infinity, our function tends towards, it goes up and up and up and up, so it tends towards positive infinity. On the right hand side, as I approach positive infinity on the function, the y value approaches positive infinity as well. Let's look at example 5. Alright, as I draw this graph with my pen, I have to lift the pen at negative 4 and actually jump the pen down. So there is a jump at x equals negative 4. And I then continue my pen until I get to this point, and there's a hole at x equals positive 2. My left end behavior, well, the function doesn't exist out here on the left-hand side, so there is nothing to say about the function not existing, or there's nothing to say about where the function approaches, so left end does not exist. And the right end, as I approach infinity, the function, as we go further and further to the right, the function goes further and further towards negative infinity. Example 6 is another polynomial. Here we've got this curve. There are no gaps, so there is discontinuities? None. There are none. Like the previous polynomial, both ends go up. So when we discuss the end behavior of the left side and the right side, both sides tend towards positive infinity. Okay, example 7. This graph has a jump discontinuity located at x equals 3. And the left side end behavior doesn't exist, and the right side end behavior doesn't exist. So going out towards negative infinity, we can't talk about what the graph is doing because it doesn't exist. And going out towards x equals positive infinity, can't talk about because the graph doesn't exist. Okay. Example 8. Looks like as I draw example 8, I have a jump in the graph. So there is a discontinuity. This is a jump at x equals -1. And then I continue drawing, and again I have a jump at x equals 3. So there are two jump discontinuities, one of them at -1 and one of them at 3. Like the previous graph, nothing is going on out at the left-hand side and the right-hand side, so the end behavior does not exist. When we get into a unit on limits, we will talk more deeply about limits at numbers other than infinity and negative infinity. For example, we could discuss the limit as x approaches 3, but we're not doing that in this unit. Example 9. Here we've got another polynomial. Polynomials are great because they have no discontinuities. They exist everywhere. Their domain is from negative infinity to positive infinity. The left end behavior, as we go way to the left, the function tends towards going further and further down to negative infinity. If we go right on the graph, the function tends to climb without bound towards positive infinity. Example 10, this one again, this is a slightly smaller graph. We're going to draw an arrow there and an arrow there so that it's easier to read. We have a couple of discontinuities. So as I'm going along, my first discontinuity, I have to lift my pen to drop to this location. So we have a jump at x equals 0. Then we climb, and then there's a vertical asymptote, so we have a infinite discontinuity at x equals 2. And then again, coming back down, we have a hole at x equals 3. So there are 3 discontinuities. 1, 2, 3. 2, 3. 3 discontinuities. The left end behavior, Oh, this is nice, a nice change. As we go towards negative infinity, our function tends towards a value of 0. You can see this is getting closer and closer to the horizontal asymptote at 0. On the right-hand side, as we tend towards positive infinity, our function tends towards a y value of negative 3. That's a great example for these concepts. Example 10. Example 11, discontinuities and end behavior. We've got a couple discontinuities going on here. We've got a discontinuity, I'm going to call it a hole at x equals negative 4. We've got a jump at x equals negative 2. We have another hole and at x equals 0. And then we have an infinite discontinuity at x equals 3. Hole, jump, hole, infinite. The left end behavior doesn't exist because the function doesn't exist out towards negative infinity. And the right end behavior, also the graph stops existing, so as we go towards the right side, the function ceases to exist. All right, finally, example 12. Discontinuities, we're moving along. We've got a hole at x equals negative 2. Another hole at x equals negative 1. Then we have a jump at x equals 1. And an infinite discontinuity at x equals 3. And like the previous example, both endpoints, they end the graph, so we can't talk about left end or right end. The functions don't exist out there. So the right end and left end behavior both do not exist. All right. This concludes the portion of the video on discontinuities and end behavior. And the last and fifth part of the video will be on Extrema. All right, welcome to the fifth part of our video series on graphical behavior. In this video, we're going to be looking at local and global extrema, being the maxes and mins of the graphs. Local extrema are points that are locally extreme. So if I were to look at this location and this location here, those are low points in their local vicinity, and this point here is a high point in its local vicinity. So let's write those down as sentences. We have a local maximum, so at x equals 0, a local max of 3 exists. For our local minimums, we have 2 of them, being those orange dots. At x equals negative 2, I'm going to use the backwards e. There exists a local minimum of negative 2. And then at x equals positive 2, there exists a local minimum of 1, 2, 3, negative 3. So that's our local extrema. For absolute extrema or global extrema would be what is the highest high or lowest low. And so for these two, there is at most one global maximum and at most one global minimum. So when I look at the global maximum, how high does the graph get? Well, this graph goes up forever, so there is no global maximum or no absolute maximum. The graph is unbounded, it goes up to infinity. As far as the absolute minimum, the lowest point it gets to is this singular point right here. So at x equals 2, there exists an absolute min of negative 3. So those are our local and global extrema. We'll shift up to example 3. Example 3, again, we've got a low point right there, and then I'm going to circle the high point in purple. So we're looking for the absolute maximum at x equals negative 2. There exists a local max of the y value at that point as 2. There are no other locally high points, so now we move on to locally low points, or minimum, and that orange one. At x equals 0, there exists a local minimum of negative 1. Then we'll go to our global extrema. The highest point the graph gets to is right there, and the lowest point the graph gets to is it just keeps going down and down and down and down. So because it goes down without bound, there is no global minimum, and our global maximum happens at x equals negative 2. There exists a absolute or global maximum of 2. So it is possible for local maximum to be absolute maximum. That is usually going to be the case, but not every local maximum is an absolute maximum. Okay, let's look at example 5. In example 5, we'll highlight the low points. There are no low points to highlight. There wants to be one here, but it's an open circle, so we're not going to include that one. As far as high points, we have 2 high points. I would call this a local maximum, but it doesn't exist on the left-hand side of the point, so we can't really refer to that as being higher than the area to the left. So let's discuss our local maximums. At x equals 0, there exists a local max of 4, and there's also at x equals 4, there is a local max of the y value is also 4 for that one. So that one's got 2 local maximums. For local minimums, no low points, so we'll go with none. For absolute maximums, the highest value that we get is right there, And the lowest value that we get, well, the graph keeps going down and down and down and down. So we can write out our global extrema as at x equals -8, there exists an absolute max of 6. That's the highest it gets. It's also going to be the highest value in the range. The global minimum, well, this thing goes down forever, so there is no global minimum. It's like saying the minimum is -infinity. Well, there's a number smaller than -infinity. It's -infinity minus 1. So okay, example 7, good, easy, clean, friendly graph. We've got, that is a local minimum. This is a local maximum. And then I'm going to go ahead and classify this one as a local maximum too, because to the left we are above and to the right we are above. So we've got 2 local maximums at x equals 3 and at x equals 4. 3 and 4. There exists a local maximum of 5. There exists a local max of -3. For our local minimums, at x equals -1, there exists a local min of, the y value at that point is -1. For the absolute extrema, the highest that we get is 5, and the lowest that we get is -5. So those identify our absolute extrema. So our absolute max is at x equals 3, there exists an absolute max of 5, and at x equals 5, there exists an absolute min of -5. Our global extrema should align with what we've got for our lowest and highest numbers within the range. That should always be true, the lowest and highest numbers in the range. Okay, example 9. We're getting a little bit busier with this graph. We've got a low point here and a low point here. And then we also have 2 high points. So let's start with the high points. At x equals -3, as well as at x equals 0.75. There exists a local maximum of, probably goes up to a height of 40, and our second one goes to a height of probably 15. For our local minimums, at x equals -1 as well as at x equals 3, we have our local minimums. And both of those are at a y value of 0. The highest the graph gets is infinity, and the lowest the graph gets is -infinity. So there is no absolute maximum or absolute minimum because it grows without bound in both directions. And the last example, our crazy graph number 11. There's going to be several points to look at as we're moving along. I would call this a local minimum. Again, those spots are a little bit iffy. Some people may or may not classify that as a minimum. But by the definition that I use, I think that classifies as a minimum. And then we hit a max, a max, a max. So there's only one local minimum. At x equals -4, there exists a local minimum of -1. Our local maximums, we've got one here because it's higher than a spot to the left and higher than a spot to the right. We also have one right here, and we also have one right here. So we have 3 local maximums. One at x equals -2, one at x equals 1, and one at x equals 4. The values of those, again, we need to look at the y coordinates. Our first local maximum happens at a y coordinate of 3. Our second one happens at a y coordinate of 1. And our last one happens at a y coordinate of -1. The highest point that the entire graph gets to is right there. And the lowest point of the graph is this thing goes down to infinity, down to -infinity. So because it goes to -infinity, there is no minimum. It just keeps going down and down. It's unbounded below. However, there is an absolute maximum. The highest this graph gets is at the x-coordinate -5. There exists an absolute max of 4. Okay. That concludes the video series on graphical behavior. There's definitely more exploration of graphical behavior done in a calculus class where we do all of this analysis from an equation rather than a graph so that we can ultimately draw sketches of graphs. But when all is said and done, if you've watched all 5 videos, we should have all of the blanks filled out for all 12 examples. So thanks for watching. Be sure to comment, like, subscribe, ask questions in the chat, and have a good day.